happy to be here. Yeah, I chose this topic, Newton Okounkov body for cluster varieties, quite spontaneously. Actually, first I planned to talk about something else, but then I realized this might be of interest to the audience. So I will start with a motivation as a little warm up. So I will be speaking about cluster varieties, as the title says. And even though if you're not familiar with them, although I see many people in the audience that for sure know about them already, they're interesting because they appear inside many varieties that probably you would care about. My favorite examples are Grassmannians and partial flag varieties, but there are more from representation theory, like configuration spaces, double Bucha cells, but also the Del-Pezzo surface of degree 5 can be obtained from a cluster variety, algebraic groups, moduli spaces of G-local system, and this list is probably much longer, just that those are the examples that I'm aware of. So cluster varieties, or their cluster structures, say, can be used to obtain toric degenerations. And the first construction here was given by Gross Hacking Keel Kontsevich in their paper that was published in 2018 for one type of cluster variety, but we will see that there's a dual notion, and the dual picture was established by my collaborators, Nachela Chavez, Magui, Frias Medina, and myself in 20. And now coming to Newton Okounkov bodies, I'm assuming that all of you are more or less familiar with the idea of constructing toric degenerations of projective varieties using Newton Okounkov bodies. So the leading question for this talk will be if there are Newton Okounkov bodies for cluster varieties. And well, to get to that point, to tell you, so the answer to the question is yes, first of all, that's why I'm giving this talk. But to tell you how exactly, I'm gonna take the first half of the talk as a lecture on cluster varieties and their compactifications. If you're familiar with the topic, I'm sorry, you can take this as my setup of notation. But after this first half, we will get to the point where I can tell you about the intrinsic Newton Okounkov bodies that we can associate with cluster varieties. And in the end, I want to get to examples and kind of line out a bit how you get back to usual Newton Okounkov bodies in the cases of Grassmannians and partial flag varieties where they have been studied extensively. So let's just get started with cluster varieties and the first part, tropicalization, a certain conjecture, and the wall and chamber structure. So cluster varieties, from a geometric point of view, are like a generalization of tori in some sense. So I'm going to take advantage of that and use usual toric notation. So I'm going to always have a lattice n that is isomorphic to z to the n, and it's going to be equipped with a skew symmetrizable bilinear form. So this form can also be skew symmetric. In that case, you can combinatorial think of it as being encoded in a quiver. M is my notation for the dual lattice. And then all the theory of cluster varieties really evolves around certain maps that are birational maps from the torus Tn to itself that are called mutation. And they are defined as pullback associated to two lattice points, n and m, n being in the lattice capital N and m in the lattice capital M. And then for a monomial z to the m prime, so a function on the torus Tn, this is the output of my mutation formula. So it depends on m and n, the two in the index. Now, a first exercise to do is if I fix now a basis for my lattice n, and this will also be very important, I will throughout the talk have seeds and seeds. A seed is always a lattice basis for the lattice n, and then it comes along with a dual lattice of m, and it comes along with these elements vi that are also elements in the dual lattice that are simply obtained by plugging in ei in my symmetric bilinear form in one component and leaving the second empty. So first exercise is to see if we tropicalize this mutation for now the very special choice of lattice points, will take minus ek, an element of my basis, and vk, the dual obtained from the bilinear form, then this tropicalizes with max plus convention to a pseudo-reflection on the lattice n. And moreover, if I plug in all my bases into this pseudo-reflection, I will get out another basis. And this will be another seed. So having this set up briefly, say.
What a pseudo-reflection is?
Oh, a pseudo-reflection is a combination of a reflection and a shear. So it's, yeah. Okay, so yeah, so given this setup of notation, I can define cluster varieties. So cluster varieties are glued from tori. There are two versions of them, just as we have a torus and a dual torus, we have a cluster variety and a dual cluster variety. The A variety is glued from the tori Tn. And I'm going to glue always along these mutation maps, where the elements I plug into here, like the choices of mutation, would always be of this form, minus ek vk, and then I'm going from one seed to another using these pseudo-reflections. And for the X variety, I'm going to do the dual thing. I'm going to take the dual tori, and I'm going to glue them along mutations that are dual in a certain precise sense, but that would be another exercise. So I glue here along the mutations vk, ek. So if you notice in this mutation formula, there's nothing that really prevents me from exchanging the lattices n and m. So the same formula for n and m switched works and gives me the dual mutations. As I didn't want to spend too much time of going into these mutations and these formulas, I just prepared two examples to show you what that more or less looks like. So if I start with a lattice of rank 2, Z2, and have my skew symmetric, in this case, bilinear form given by this matrix for my first choice of bases, E1, E2, then the A variety is glued from 5 tori. And if I take always the coordinates of these tori and express them back in my initial coordinates that correspond to the monomials in terms of the dual basis, then this is what I get. And one observation you can make here is that all the coordinates, so this is also the toric notation, so z to the f or z to the some lattice element is the monomial in the variables z1 to zn. And all of these coordinates that appear here are in fact Laurent polynomials in my first coordinates. So if I go to the X variety, this picture changes a bit. At least I lose the Laurent property of all these coordinates. The torus is also glued, the cluster variety is also glued from 5 copies of the same torus, but the coordinates and the gluing maps change. Okay, if you have any question at any point, please feel free to interrupt. Okay, so this is the first baby example of cluster varieties. And what I will do with these cluster varieties to establish the whole theory is first of all tropicalize them. So if you have a look again at the mutation formula, then one thing you can note is that it is subtraction free. So I'm only using multiplication and addition in this formula. That means in particular that this formula still works if I'm not working over a field, but over a semi-field. And so for a semi-field, we define the P, for a semi-field P, we define the P points of the torus Tn, just as in the case of fields, as the tensor product of the lattice n over the integers with the semi-field. And this enables us now to look at also the cluster varieties over a semi-field. So what A of P and X of P here would be is simply taking the tori now with the semi-field points of the tori and gluing along the mutation maps that are valid over the semi-field as well. And this, in the end, boils down to giving us non-canonical identifications of these of the cluster varieties over the semifields, with also the lattice tensored with the semifield. But we have this kind of identification for every choice of seed S. And because the coordinates change along every mutation, this identification is different in every seed. And also the cluster varieties themselves, they don't have a lattice structure. So for me, the most interesting tropicalization is the one over the integers, the rationals or the reals, and the semifield contained in them. So ZT or QT or RT will always be, well, the integers with max and plus as operations, or the rationals or the reals. And these kind of tropicalizations of the cluster varieties, well, will play an important role. And now here we are in this case where, well, if I take the tensor product of the lattice with, for example, the tropical semifield in the integers, that is just again the lattice, but this identification is an identification as n torsos. Like on these cluster varieties, I do not have a lattice structure. Okay, are there any questions about this? Okay, so then let's move on and see why these tropicalizations are important to the theory. If we recall from toric geometry, that the torus Tn has a dual torus, Tn, and the integer tropical points of the dual torus, well, as I've just defined it, are simply the torus, the lattice tensored with the integers. So I get back the lattice. And in particular, the tropical points of the dual torus parameterize the basis of regular functions for the original torus. So in toric geometry, these are simply the characters of the torus. And now, as cluster varieties are, well, kind of far generalizations of tori, but you can imagine that it's not too bad to hope for a similar statement for cluster varieties. And this was what Fock and Goncharov expected and conjectured. So the version for cluster varieties goes as follows. The tropical cluster variety, the tropicalization of X, or respectively the tropicalization of A, was conjectured to parameterize a basis for the regular functions on the dual cluster variety. So the integer tropical points in the X variety expected to parameterize a basis for the regular functions on the A variety and vice versa.
Just to make sure, the A and X variety, are they assumed to be, are they all known to be affine or not?
No. So no, the X varieties are actually relatively wild. Like besides some very small examples, they're non-reduced schemes. The A varieties are a bit better behaved. And we will mostly see A varieties also throughout this talk and the examples. So the examples I mentioned, the Grasmanians and the flag varieties, all of them contain an A-type cluster variety that has, for example, this property that all the cluster variables, the coordinates of the tori, are Laurent polynomials in the initial choice of coordinates. That makes them more approachable, say. So, yeah, one thing that is important to mention along with this conjecture is that it is false in general. So there are counterexamples, actually of quite small dimension, 3-dimensional A cluster varieties, where this is simply not true. So if you're familiar with the subject, it's the Markov quiver that gives you here an A-type cluster variety where the conjecture does not hold. However, this conjecture is true in the interesting examples. So in the examples like the Grassmannian or the full flag variety configuration space, we do have this conjecture, and it gives us, of course, a very good tool, like a solid solid information about the regular functions encoded in the tropical dual cluster variety. So there's another formulation of this conjecture, which is usually referred to as the full Fock-Gontreff conjecture. And we say that the full Fock-Gontreff holds for the A variety if the lattice points inside the tropicalization of the X variety and their associated theta functions are actually a basis. So the difference here is that we go to an algebraic level. Gross Hacking Keel Kontsevich gave a construction of how to associate theta functions to points in this the two integer tropical points of the X variety. And I will not give you the construction here. We will see one ingredient of the construction briefly appearing that are broken lines, but it is a kind of algorithmic way to construct functions on the A varieties. And where in this case, so the second ingredient necessary here is, well, we need to construct these theta functions. I'm going to leave that as a black box. And the second part of this conjecture, why it is a stronger version, is that they actually form an algebra. And that this algebra in the end is the algebra of regular functions on the A variety. So for my applications, for my examples, it will be necessary to have this conjecture, but it is satisfied in the cases that I'm going to talk about. So if we now recall by the definition of these integer tropical points, we have the identification of the tropical points of the X variety with points in the lattice M itself. And where this kind of a nice setup where it's quite natural, I think, to consider the following mapping that actually given a seed, so all these identifications always depend on a seed, a fixed chart for the cluster variety, and given one of them, we can simply assign to a basis element theta m the tropical point, which is now actually a lattice point in M. And together with my collaborators, Mandy Cheung, Timothy McGee, and Alfredo Nájera Chávez, we showed that this extends to evaluation. So whenever talking about valuations, now I should give you some information of what is the order I choose on the lattice M. But in this case, there is actually no choice. So the lattice M comes with a natural partial order that is called the dominance order. And it is essentially a pullback of simply the division order we would have on the monomials whose exponents are in dual lattice. And given that partial order, whatever refinement, whatever linear extension we choose, this boils down to the evaluation. So these will be the valuations that we use to construct Newton Okounkov bodies for. And a few comments are in place at this point. So first of all, by work of Naoki Fujita and Hironori Oria, there's a similar construction. They have evaluations that similarly use G vectors. That's why my index here is G, because there's the notion of G vectors coming from Fomin and Zelevinsky's principal coefficients. And this valuation is an extension of this concept. And it also appears in work of Fujita and Oya. However, this proposition is what I'm stating here is a very small example of it. It extends also to the dual setting for X varieties under certain assumptions. And it will boil down to compactifications as well, as we will see in a bit. And moreover, this construction is closely related to the toric degenerations of Gross Hacking Keel Kontsevich that I mentioned in the motivation slide. So in this setting, for simply the A variety, Gross Hacking Keel Kontsevich, give a construction that would degenerate the A variety to the torus it is built from. And this valuation in this context would do the same thing. Okay, I think this was my last slide on the non-compact guy. Oh no, wait, I'm still going to tell you about the wall and chamber structure on the tropical real points of an X variety. So these theta functions, I'm sorry I leave it so much as a black box. This slide is intended to give you at least some examples of what these functions are. So if we choose one seed or equivalently one chart to the cluster variety, and let's say its elements are E1 prime to En prime, and it's still basis for M. So remember, a seed is always a basis for the lattice N. The dual basis for M indexed by the Fs. Then I can consider any kind of monomial inside in these coordinates of my seed corresponding, my coordinates corresponding to the seed S prime. So what I mean by that is taking a monomial with exponents that are lattice points in M that are positive combinations of my basis. So this is any lattice point inside the positive orthant. And these monomials turn out to be part of the theta basis, and they are called cluster monomials. So these are monomials, like honest monomials, not Laurent monomials, that are simply combinations of the cluster varieties, cluster variables of one seed. And their G vector, so the valuation, the tropical point associated to this very simple theta function is simply the lattice point it corresponds to when I'm in that same seed, so expressed with respect to that same seed. And now there's a wall and chamber structure on the X variety. So remember, these are points that lie in the tropicalization of the X variety, as I'm picking my Fs in the lattice M. They generate a wall and chamber structure here as follows. So what I can do now is I take the positive orthant with respect to one of these seeds as prime, and I'm going to pull it back along the mutation formula to my initial seed as 0. And it turns out that all this pullback preserves, although they are shear maps, they are pseudo reflections, but they preserve this cone, and it stays a simplicial cone. And in the end, if I take the union over all seeds and all these pullbacks, I do get a simplicial fan. So I'm stating this here as if it would be quite clear, but this was one of the very a long-standing conjecture. So this was observed already by Fomin and Selevinsky in their very first paper and verified for the first cases. Then there was some partial results throughout the years by, for example, Cerulli, Irelli, Keller, Laberdini, and Plamondon. And in full generality, it was proved in the paper published in 2018 by Gross Hacking Keel Kontsevich. So this simplicial fan can be extended to what is known as a scattering diagram, and that gives the full wall and chamber structure on these X varieties. So let's have a look in an example, at least, of what these theta functions are. If you remember, this is the picture or the fan that I had drawn already for the A and X varieties in the very first example. So along the rays here, the first lattice point will always correspond to the theta function that is just the coordinate associated to that orthant. So every orthant here, remember, corresponds to a torus chart. And along the rays, you would find the coordinates corresponding to that torus chart. So in my first case, it was just the two variables, z to the f1 and z to the f2. And as I have expressed everything here in my first in the coordinates of my first chart, if I run through the rest of the diagram, well, I encounter other variables. For example, along this -1, 1 ray, my theta function is the coordinate associated to the mutation of the z to the f1, and it is a monomial, a Laurent monomial in the initial seed. And now all the lattice points inside these cones, they would just correspond to the corresponding combinations, the monomial obtained from these ray generators, from the coordinates on these rays. And all of this takes place in the dual cluster variety in the real tropical points of the dual. Okay, so then let's move on to compactifications. There are many ways to compactify A cluster varieties. I will talk about one specific case that is in terms of freezing variables, just because it will be the one that applies to my examples. So if I take again my initial data, my initial seed, my initial basis for n, I can declare some of those variables, some of those basis elements is frozen, and that means that I will simply never mutate in these directions. So remember, my mutation always depended on one of these basis elements, and I will simply never perform mutation in these directions. So consequently, on the A variety, it is now possible to allow the corresponding cluster variables to vanish. So if I mutate at a variable, I divide it at the corresponding cluster variable at some point. If I never do that, I can extend my cluster variety by allowing these to vanish. So for example, if I do this in my running example, and if I now declare the second basis element E2 to be frozen, then suddenly I only have one possibility left to perform mutation, and my A variety is glued from only 2 tori that correspond to these 2 chambers from the second slide. And the partial compactification, where now I may add a divisor to it that allows this second cluster variable z to the f2 to vanish. So I will be gluing not 2 tori, but 2 copies of c star times c along the biggest open part where my mutation is still defined. And the difference between the compactification and the A variety itself is a divisor that is called the boundary divisor. So in the spirit of mirror symmetry, a compactification on one side now should give me a potential on the other side. And part of Gross Hacking Keel Kontsevich's program is to give a construction of such a candidate potential. So the potential function should now be a function on the X variety. And it is associated, like it has summands associated to each component of my divisor. So remember, in my setup, the divisor consists of these, of simply the vanishing of one cluster variable. And I have, well, from K to N, many of those. Now, given some mild assumptions that, in fact, it has been announced that these mild assumptions are always fulfilled. So you might as well ignore it in a few months. Hopefully there's a paper that will tell you you don't have to assume anything anymore. But the idea here is that we are allowed to identify tropical points with divisorial discrete valuations. So each of these divisors on the A variety gives me a divisorial discrete valuation just in terms of the order of vanishing along this certain component of the divisor.
Can you maybe say why this isn't sort of an obvious statement? I feel like on a torus, that's kind of obvious. And what's difficult here?
Yeah, so the point here is that, so what this needs is what is called the symmetry of the tropical pairing, right? So on a lattice, we have the pairing of where we have the usual lattice pairing of n and m, but we can also interpret both of them, like lattice points, as functions on the other, right? And then what we can do is we can either take the function z to the m and evaluate in n, or the other way around. So we can swap the order, and this does not change anything. So we can take the order of vanishing along the divisor defined by one function and evaluate in the other function, or we can do it the other way around. Right?
Yeah.
Yeah. And so this symmetry, it is a priori not clear why this should extend to all of the tropical space. So whenever you choose a lattice identification on that torus chart, obviously it is true, but what has to be checked is that it is also true after changing the chart, that it is globally true.
So the statement is that it's even after changing the chart, it's still a divisorial valuation. I mean, it's got to be some valuation no matter what, but it might not be divisorial. Is that the statement?
So the statement is, if you take the order of vanishing along one di that I now think of as a divisor defined by a lattice point in A, and you evaluate on a theta function on x, then that is the same as swapping the position. So every tropical point in both spaces is a function and a divisor at the same point, and I want to be able to swap. So,
I see. Okay, great. Thanks.
Yeah. No, thank you for the question. Yeah, but it has been announced by actually Timothy McGee together with Travis Mandel, and I believe Mandy Xiong, maybe I'm forgetting another person. It has been announced that so they have something they believe will prove this in full generality. But yeah, so the problem here, as all the problems actually in cluster theory, occurs that whatever you expect, it should be it should hold also after mutation. Great, but so we're very optimistic now. I'm very optimistic, and I will assume these mild assumptions from the start. And the reason is also that in my examples, this is true. So there's no known counterexamples to this symmetry statement. And well, once I have all the symmetry, what I will do is this chain that I drew out here. So I will I will take the order of vanishing along my divisor component. I can now associate it with a tropical point in A, and then that one I can also associate with Gross Hacking Keel machinery, a theta function on the X variety. And my potential is simply going to be the sum of these theta functions. So I wanted to at least give you a bit of a feeling of how this potential looks like in some specific chart. And there's some combinatorial hypotheses that are not too hard to verify, but also depending on your example, it might get a bit tricky. And it is known as the optimized seeds. So essentially, what you want if your form would be skew symmetric and given in terms of a quiver, you would want to find for every frozen direction one seed where this particular vertex is a sink. And if such a seed exists as prime, say for some of index I between k and n corresponding to a divisor, then in those particular coordinates, my theta function will simply be the inverse of the corresponding coordinate on the X variety. So it will be z to the minus ei prime. And well, given that, I can mutate back along whatever sequence to whatever seed I feel like and get an expression of my potential in that seed. So if we go to our baby example, then so here I decided to never mutate in the direction E2. So my divisor was z to the F2 is z equals 0 on the A variety. And it turns out that not in the initial seed, but the other seed, the corresponding vertex of the quiver is a sink, or said differently, in the second chart, my theta function corresponding to this, oh, this should be a 2, sorry, corresponding to this direction would just be the inverse of the corresponding cluster, the corresponding x coordinate. And if I mutate back to the first seed, I get an expression of this form. And in fact, if this combinatorial hypothesis is satisfied, my superpotential will always be a Laurent polynomial with terms such that its enumerators are 1. And at this point, first I thought I should give you this as an exercise, but then maybe it's been a lot of information already. So if you remember this cone that I have drawn out before, so this actually in this case the scattering diagram for the X variety, then you might notice that the monomials in my superpotential are exactly corresponding to the hyperplanes that define my cone. So in other words, if I take this cone and I tropicalize it now with respect to min plus convention, and I consider all the points that are less or equal to 0 when evaluated, then what I get is exactly this cone. And this is the function of the superpotential, if you like. So inside the big scattering diagram, the big X tropical space, the superpotential, if all the assumptions are there, should cut out the part of the tropical space that corresponds to points which are still functions on the compactification. So let's write this out a bit more general. My X tropical space is now still identified with the lattice, and inside the theta basis that for the non-compact cluster variety consisted of all theta functions associated to simply all lattice points I have in the X tropical space. Now in the compactified case, the superpotential is used to cut out parts of this space X trop, such that the lattice points in that cone or in that region, say, still correspond to functions on regular functions on the compactified cluster variety, and moreover, they should form still a basis. And for this to work, I need the combinatorial assumptions and the mild assumptions. So from now on, we will be working with cluster varieties where this is satisfied, as it's also satisfied for my examples. And by psi s, I will denote the cone I get. So it will be the intersection of the tropicalized superpotential with the integer points, and then realized with respect to my choice of seed. So I get a cone inside MR. So that is my notation for the lattice tensor R. Okay, so now in this setting, we can go back to our valuation, and we can formulate the same proposition now for the compactified cluster variety, or partially compactified, to be honest. And we get the same assignment. We take a theta function, we simply send it to the lattice point that was indexing it from the start. And I get a valuation now from the regular functions of the compactification. And by construction, the Newton Okounkov cone of this valuation is the realization of my superpotential potential cone in one seat. Okay, so up until here, I have collected all the ingredients to now tell you about the intrinsic version of these Newton Okounkov polytopes. So far, we haven't seen polytopes, just cones. So from now, the lecture is over. This was the background on cluster varieties necessary. So let's get into the more interesting stuff. I have mentioned this already before, and I tried to line out a bit the structure that these X tropical spaces have. So I mentioned these identification with the lattice, of course, are non-canonical, because the X tropical spaces are not lattices, the integer tropical points in them, but they have a wall and chamber structure. They are actually integral affine manifolds, if this means anything to you. But the wall and chamber structure is essentially the most important ingredient we have. So it allows us, or it allowed Gross Hacking Keel and Kontsevich to define a notion of broken lines inside these spaces. So whenever I think of this space now as being identified with a real vector space and the lattice M inside of it, this wall and chamber structure, or the broken lines inside it, will be piecewise linear functions that are linear inside all of the chambers. So the cones, my simplistic cones that I collected from these positive orthons, but the structure here is a bit more complicated. We have additionally dense regions of walls. So essentially, this wall and chamber structure consists of the simplicial fan that I told you a bit about how to get, and then the rest is filled up with dense walls. And these broken lines were introduced by Gross Hacking Keel Kontsevich as a combinatorial tool that should replace pseudo-holomorphic disks in mirror symmetry. And these broken lines are key ingredients to define the theta functions and their structure constants. So yeah, I decided to not give you the definition due to lack of time, but I'm happy to give you a bit more detail, so feel free to ask me about it later. Now, given these specific broken lines that are actually a bit more than just piecewise linear function, they come associated with monomials in every linear on every linear piece, and these inspired or allowed my collaborators to introduce a convexity notion in these spaces. So if I have a closed set in one of my tropicalized X variety, then it is said to be broken line convex if for any 2 points in the set and any broken line segment that connects them, the whole line segment is contained in the set. So as an example, I have drawn here the scattering diagram or the fan for G2. And the marked lattice points are the ones, the tropical points corresponding to all the coordinates of coordinate charts. And if I take their broken line convex hull, you can see that it spikes out here in the top and actually is a bit bigger than the convex hull. So this will always be the case. Maybe let's make it a bit bigger. This will always be the case. In fact, the broken lines are such that, well, they are only allowed to bend at walls. And additionally, the straight line going through the wall is always a possible bending. So there's some additional information at the walls that controls the ways how my broken lines can bend when they hit the wall. And the straight line is always possible. So in particular, a broken line convex set always contains the convex set. And the broken line convex hull of a fixed set of points. And additionally, also afterwards, like after realizing in a seed, a broken line convex set will be convex in the classical sense. The only difference is really that when I take the broken line convex hull of a certain set of points, it might be a bit bigger than the classical convex hull. And oh no, now I made it very small. Huh? Let's try to make this good size again. Okay. Now these broken line convex sets are very important, or like are key in the cluster theory, as they extend the analogy of toric varieties and cluster varieties. So my collaborators showed that for any compact set S inside the real tropicalization of the X variety that is broken line convex, it defines a projective compactification of the A variety. So this is really the classical analogy of compactifying a torus Tn by a polytope. Here we can compactify the cluster variety A with the broken line convex set. And this compactification is also just as in the toric sense. So the lattice points, the integer tropical points inside the broken line convex set give me a certain collection of theta functions, and I take this collection to define a graded ring. And if my set is broken line convex, then it tells me that the theta functions I have inside this set behave do define a graded ring if I simply extend by dilation. So in particular, if I take two theta functions corresponding to two different dilations, say A and B, and I multiply them, then I know there's going to be the product, all the theta functions in the product, or the leading theta function in the product will lie inside the A plus B dilation of my set. Okay, so given this notion of convexity, we are now free to start with the construction of the intrinsic Newton Okounkov bodies. So again, I will assume that all my conjectures hold. I really need the theta basis to be a basis for regular functions. And if I'm in the setting, then I can write any regular function simply as a combination of theta functions. And the first step here is to define the theta function analog of a Newton polytope, or the theta Newton polytope, which is now the broken line convex hull of all the tropical points, such that the corresponding theta function appears with non-zero coefficient for my regular function. And well, in my ambient space, of course, is the real tropicalization of X. And then given this notion of Newton polytope, I can go further and consider a Newton Okounkov body. So say I have a line bundle L on my compactified or partially compactified A variety, and R of L its section ring. Then the intrinsic Newton Okounkov body is really simply taking the usual definition of Newton Okounkov body. The only thing I replace now is that instead of having a valuation, I will take here the theta Newton polytope for my regular function. So I run through all the gradings, all the graded pieces, I run through all the elements, and for each degree J, here I take the broken line convex hull of the exponents or the tropical points corresponding to theta functions in my extension. And the result is that if I now have my G vector valuation, and we will see in a second how I can here magically swap from regular functions to section ring, but assuming I have my G vector valuation defined on the section ring, and I have identified with respect to my seat S the X tropical points with the lattice, then this identification of the broken line convex hull of the intrinsic Newton Okounkov body boils down to being the actual Newton Okounkov body for the G vector valuation. And
sorry if I may interrupt. Here you do need to take union over all J, yeah? All the graded pieces, unlike the toric case. In the toric case, you just take convex hull of, yeah, okay.
No, I know, I really do need this union. Mm-hmm. Yes. Yeah, it is as in the case for Newton Okounkov bodies for projective varieties. So whenever for project, not only.
I mean, do we even know that the section ring is finally generated? We probably don't, right?
Well, this would be assumptions we would have to make. Like, yeah, we will.
But if you don't know, then it's a very natural step to take all J.
Yes.
So it's safe this way.
Yeah. So yeah. Let's see. I mean, there's many open directions when it comes to this, and many open questions. And one reason actually why our paper is still not available is that we're still looking for like say the best assumptions to consider these objects. Because in our example, we will see now the examples are the very nicest cases where everything happens as you expect, say. But there's certainly possibilities to go away from such nice cases. Okay, so let's go maybe to the examples and see what are the advantages, or what are the advantages for me, say, of these broken line convex hulls. And we will see that this broken line convex hull, as I've shown you in this small example already, as it can be a bit bigger than the classical convex hull, it can happen that in usual convex geometry, you add in vertices to your polytope. And for Newton Okounkov bodies, or for Newton Okounkov polytopes, this is certainly a great advantage, because you can consider the Newton Okounkov body as a convex hull, broken line convex hull of a smaller number of valuations of elements. So we got to this notion of intrinsic Newton Okounkov bodies by studying the Grassmannian. So the Grassmannian is a compactification of a cluster variety, or it's universal torso as a partial compactification of the cluster variety. More precisely, we're in the setting where this partially compactified cluster variety, its ring of regular functions coincides or is isomorphic to the Cox ring of the Grassmannian. And there's been lots of work done around the Grassmannian and these kind of cluster duality or mirror symmetry things. The first thing to note is that the dual cluster variety can also be interpreted as sitting inside a Grassmannian, and in this case it will be the dual Grassmannian. So here we have the Grassmannian k over c to the n, and now we have the Grassmannian n minus k over the dual vector space. And Marsh-Reach were among the first people that studied mirror symmetry for the Grassmannian, or that actually had developed a program and proved mirror conjectures. And in that context, they write down a Plücker potential that is defined on an open part of this dual Grassmannian. And a few years later, Reach and Williams came along, and they took this cluster structure to define full rank valuations on the Cox ring of the Grassmannian, or the homogeneous coordinate ring with respect to the Plücker embedding, with respect to every seed. And they showed that the tropicalization of this Plücker potential of Marsh and Reach turns out to be the Newton Okounkov body for that valuation. And in fact, it is an equality. This should be equal. It's not an isomorphism. They're on the nose equal polytopes. So we wanted to understand this picture from the point of view of the GHKK program. So to do that, I need to tell you about one more ingredient. So these cluster varieties, with all of their duality, and essentially because of the skew-symmetric form I have on the lattice n, they come with a whole family of maps between them that go from the A variety to the X variety. So they are defined on a chart always by the skew-symmetric form, only that you have a certain freedom to choose what this map should do for the frozen directions. And it is a lattice map from n to m. So in the case of the Grassmannian, or in the case of the cluster variety inside the Grassmannian, there exists such a cluster ensemble map that goes from n to m, or the A variety to the X variety, that extends to an isomorphism of the Grassmannian and its dual, and it pulls back the Plücker potential of Marsh-Reach to the theta potential of Gross Hacking Keel Kontsevich. And moreover, the dual map, so if I take the dual of this lattice map, it's again a lattice map, and it goes again from the lattice n to m, and it turns out that on the level of points, so what it does, it sends the valuation, the Reach-Williams valuation of a Plücker coordinate to the G vector valuation of GHKK, or our valuation, if you want. And moreover, in all of these cases, the Newton Okounkov body, or Newton Okounkov polytope for this G vector valuation, independent of the choice of seed, is going to be the broken line convex hull of the valuations only of the Plücker coordinates. And this is the part to stress here. So as a Newton Okounkov body, as a usual convex hull, this is not true. Like the classical convex hull of the G vectors of Plücker coordinates, evaluations of Plücker coordinates, is strictly contained in this broken line convex hull. And the corollary that is quite straightforward from this is that we get another identification of the tropicalized, the polytope that is a tropicalized Plücker potential with the Newton Okounkov body of Reach and Williams, simply because the first identification, this pullback, a simple consequence is that the dual map sends the tropicalization of the Plücker potential to the tropicalization of the GHKK potential, or in this case, we have to intersect with a hyperplane. And so we get the same equality of the two polytopes. So in the last 3 minutes, I want to tell you how we can also look at partial flag varieties in this context. So in the case of the partial flag variety of type A, so we have a flag of k vector subspaces of C to the n, each the ith vector space being of dimension di. Then due to work of Geisler, Clark, and Schroer, we're in the same setting as the Grassmannian in the sense that there exists a compactified cluster variety whose ring of regular functions coincides with the Cox ring of the flag variety. And it is not too hard to then figure out what the theta potential should be. So the combinatorial hypotheses are satisfied, and we can write down the theta potential also in this case. If we now further go to the special case of the full flag variety, then Tim McGee showed in his thesis that the full Fock-on conjecture, so the stronger assumption for the theta basis to be a basis, exists. So we can apply again the G vector, this valuation. We can apply it to any section ring of the flag variety, and whatever line bundle we choose here, L lambda for lambda some dominant weight, the Newton Okounkov polytope of this valuation will be the corresponding intersection of the Newton Okounkov cone. And the Newton Okounkov cone, we have already seen that it is the tropicalization of the potential. And moreover, if you think of the string polytopes that are known to be Newton Okounkov polytopes for the flag varieties, then for every string polytope, so they depend on a reduced expression of the longest word in the symmetric group and the dominant weight. So for every such choice of reduced expression, there is a seed so that the string polytope is isomorphic or unimodular equivalent to the Newton Okounkov polytope of our evaluation. And the second part about string polytopes is true in greater generality. It has been proven to hold also in the cases of full flags of type D and type E in work of Gens, Koshevoy, and Schumann. And on the very last slide, I want to go a bit further to partial flag varieties of type A, which is still work in progress, but also in this case, there are Laurent potentials known, or they've been constructed by Batrievsky, Fontine, Kim, and von Straten, and they're defined on just one torus. So they're generalizing work of Giventhal in the case of the full flag, and part of their mirror construction is this Laurent potential function that is called F. And also in this case, it is we managed to prove that there is a certain choice of seed for the corresponding A variety, X variety, I'm sorry, that pulls back the theta potential to this Laurent potential. And there's more potential functions known, for example, in work of Reach for general partial flag varieties, so not only of type A, but for simply connected complex algebraic groups. And she already shows that in type A, her potential restricts to this potential function by Batrev and his collaborators. And given Thal's mirror construction, the potential he writes down are a special case of this one. So really this theory of Gross Hacking Keel and Kontsevich and the potentials they construct fit very nicely inside the whole everything that was known around, or potentials that were constructed for flag varieties before. There's so far always there was always some kind of isomorphism, automorphism of the tori that would identify one potential with the other. And I thank you very much for your attention. I'm sorry for going 1 minute over time. Here's a long list of references. Maybe take a screenshot. It's quite small to read them later, but also actually I wanted to share my slides, but I guess now it's a bit
Just
late.
send the slides to my email address, please. I can put them up on the website.
Okay, great. Then I will do that. Thank you.
Well, thank you. So questions? Okay, then I have at least one for you. So this broken line convexity that looks very interesting. Can you recover the results of Ricci-Williams? I mean, at least the Okounkov, Newton Okounkov body parts.
Yes. I mean, absolutely. In fact, so in their paper, there was a first version on the archive on their paper where they wanted to be the Newton Okounkov body simply to be the convex hull of the valuations of the coordinates for any choice of seed.
Yeah, well, but yeah.
That did not work. But in fact, having this notion of broken line convex hull, it works. So this is exactly the second part of the theorem. So the magic or the trick of these broken line convex hull is really that it is for any seed now enough to consider just the valuation of the Plücke coordinates and take the broken line convex hull of those. And you will know that the outcome, once you realize it then in the lattice and so on, will be the actual Newton Okounkov body.
Okay, so but broken line convexity kind of presupposes the existence of a fixed kind of wall and chamber structure, right?
Yes. So I mean, this notion is particular to cluster varieties that have this structure.
Well, I mean, not necessarily. I mean, there are many places in algebraic geometry, for instance, where you would have kind of a fairly natural wall and chamber structure with respect to which you can talk about broken line convexity. What would be the equivalent of a simplex with respect to broken line convexity? How does like a broken line simplex look like?
Well, would your simplex be in just one chamber?
No, I mean in general, I mean, that's the point, right? I mean, if it's in one chamber, then it's a simplex.
Yeah. Well, it's fairly hard to say something general. So there is cases, for example, if you think of this the type A example in the beginning, then broken line convex hulls turn out to be convex hulls. So the thing is really always if it's possible to have this bending that goes further out, like here, like in this example, if it is possible to have broken lines that are further out than the point you already have, right? So this can happen, for example, in this case in type G2, but it cannot happen in type A. So it is specifically about the wall and chamber structure. And here wall and chamber structure means that the walls have this extra information of a bending parameter and a wall function associated with them. And it always depends on what is the information, what's the input of the broken line that comes to your wall and how it is related to the information of the wall. And the possible bendings are determined by both. It depends on this wall function and on the input that you have from the broken line.
Okay. Well, thank you. Further questions?
Sorry, this is a vague question, but is there any relation between this broken line convexity and convexity in buildings? Or because it kind of looks
that's
like...
a very nice question. Unfortunately, I don't know enough about convexity in buildings to give you any kind of answer.
Sorry, one just clarifying question. Because I'm not sure about the assumptions for this in this situation, but it's possible that this Newton Okounkov body under this broken line convexity be something infinite. Yeah, you can have infinite walls and chambers and so on, or does it make sense?
Yes. Yeah, I guess it goes a bit in the direction of Alex's question, right? What are the section rings we look at, and if they can be non-finitely generated?
But saying the example of Grassmannian it's something finite, yeah, like
Yes. Yes, yeah. So in the examples of the Grassmannian and flag varieties, it's going to give you something finite, and I don't know an example where it gives you something infinite.
Thank you.
No, thank you for the questions.
So further questions? When not, then let's thank the speaker again. And we will meet in precisely